Hi, welcome everyone. I am Dr. Rajkumar from School of Physics and Material Science, Thapar Institute, Patiala. In this video, we are going to talk about random walk. As it is clear from the name that the steps which are randomly taken in any direction is a typical example of random walk. So this figure, it shows a kind of random walk taken in different directions, uh, and it is to be considered that the probability of going in any direction will be same. Okay, so the topics which are to be covered in this video are introduction to random walk and mathematical model of random walk. So this concept of random walk first introduced by Carl Pearson in 1905. A random walk is a kind of mathematical object known as a stochastic or random processes that describes a path that consists of succession of random steps or some mathematical space such as integers. Okay, an elementary example of random walk is uh, in walk on integer number line, which starts at 0 and at each step moves +1 or -1 with equal probability. So what it means that consider you are standing at origin, and you have equal probability of taking one step either to your left or right. So this is a simplest example of random walk. Many physical processes like diffusion of gas, electron transport through the metal, Brownian motion, round of errors in computers, etc., they are modeled as random walk. So let us consider an example of a drunkard man. This figure shows a drunkard man. He is not in his sense of direction and steps he is taking. So we can predict his position after taking n steps in any direction using random walk. The direction of each step is independent of previous one in this figure. So this is the another example of a random walk of a drunkard man. Now let us consider another example of a bottle of perfume opened in a classroom, and the fragrance soon drifted throughout the room. The fragrance spread because some molecules evaporate from the bottle and then collide randomly with other molecules in air, eventually reaching to your nose even though you are hiding in the last row. So even then the fragrance reaches to you. So we wanted to develop a model for this process, which we can then use as the basis for computer simulation of a random walk. So we want to make the model for this kind of walk. Once we tested the simulation, we can virtually see that uh, what the random walk taken by the perfume molecule looks like. So, and then we'll be able to predict the distance the perfume's fragrance travel as a function of time. The model we shall develop to describe paths traveled by a molecule is called random walk. Now we have used two different words, random and walk. So random because it is chance collision that determine the direction in which a perfume molecule travels, and walk because it takes a series of steps for the molecule to get from here to there, that is from one place to another place. It is also true that probably not all the processes modeled as random walk are truly random. That is, in the sense that random means there is no way of predicting the next step from knowledge of previous step. However, all the processes do contain an element of chance. So a random walk, okay, so they called a random walk, which has chance as a key element and is at least a good starting model for them. So for these kind of motion, we're talking about Brownian motion, diffusions of gas, etc. For these kind of motions. Now let us make the mathematical model of a random walk. So different area of science employ mathematical model of random walk. that predicts the average distance traveled in a walk of n steps. The mathematical model shows that average distance capital R from the origin at which the walker ends up after n steps of length 1 is equal to square root of n. So suppose you have to take n different steps, this is the first step, then second, then third, fourth, fifth, so on up to n step. So the distance, average distance is from first step to nth step is capital R, and each step has x and y components. So delta x1 for first step and delta y1 for first step again. If we add the length of each step, the total distance traveled should be n. But since the steps are not all in a straight line, so we can simply add up them to calculate distance from the starting point, because direction is involved here. So let us present a simple model for random walk in 2 dimension, that is on a plane. Okay, so which can be then extended to higher order dimensions as well, and is applicable to 1 dimension as well. So assume that the walker takes sequential steps with the direction of each step independent of direction of the previous one. uh, From the figure, it is clear that walker starts from origin and takes n unity steps in xy plane. So it is clear from this figure. I've already explained in previous slide as well. The first step has horizontal component delta x1 and vertical component delta y1, and similarly for second, third, up to nth step. So nth step has x component of horizontal component of delta xn and vertical component of delta yn. So each step is divided into component form. Now each step might be in a different direction. The distance along x and y just add algebraically, because they are components and they are in magnitude. So we are adding them in magnitude. So if capital delta x is the total horizontal distance from the origin, then delta x comes out to be sum of all the individual horizontal components of each steps up to n. Similarly, total vertical distance is delta y, which is sum of first, second, and so on nth step. Now the radial distance r from starting point after n step is shown in this figure, is the hypotenuse of right angle triangle of delta x and delta y. So we can simply write r square is equal to delta x square plus delta y square by Pythagoras theorem. And in bracket we have kept n because this r depends on the steps, n steps. So simply by taking the square root, r comes out to be delta x square plus delta y square whole square root. Okay, so we have calculated the average distance traveled. Now since random walks have chance involved at each step, so it is likely that different walks of n steps will result in different values of length r. So for example, if a man is going in horizontal direction along a particular direction, and all his steps are in that direction. For example, he is moving right only. So average distance capital R will be different in this case as compared to the man is changing its direction as well. So value of R is different for different steps or different iterations. So however, it is expected that if average over many walks, so if we have n steps, if I repeat these n steps m number of times, so average over many walks capital M, all with the same number of steps. So we have to keep the same number of steps in that. Then we should obtain an average in which some of the random fluctuations have been removed. Okay, so now we have to calculate the average. Now how we can calculate the average? Simply by summing the each component, but please note that the body or the particle or the molecule, anyone, so any person who is taking the step, he can go to right and left with equal probability. Okay, so if we consider that he is moving toward rightward as positive direction and leftward toward is a negative direction, and if we summed up, so they will cancel each other. For example, plus 1 steps in right direction, and again minus 1 step which is in left direction. So the net distance, average distance, will become 0. So it means you cannot take average of positive and negative numbers in this case particularly. So for that, for taking the average, you have to calculate the square first, then you have to take the average. Okay, and after averaging all the values, you can take square root. So you get the root mean square value of the average. So this is how average can be obtained in this case. Now let us consider previous equation and substitute value of delta x and delta y in it. So r square is delta x square plus delta y square. We are substituting the value of delta x and delta y for each step. So for first step delta x1, second step, so on up to nth step, and similarly vertical component delta y1 for first step, and so on up to nth steps. And now opening the brackets. So simply delta x1 square plus delta x2 square, so on delta x n square, and similarly delta y1 square, delta y2 square, and delta yn square. Okay, there are other cross terms as well. So delta x1 with x2, x1 with x3, and x1 with xn as well. So in between terms are also there. Similarly, cross terms for vertical component. Okay, now this equation seems to be complicated. However, if we take average of r square for a large number m of different walks, each with n steps, this number of steps will remain same, then all of the cross terms like these delta x1 and delta x2 etc., they will vanish or average out to a small number, as they are all just as likely to be negative as positive. So they will cancel each other. So we have left with the square terms only. Now the square terms like delta x square are always positive because you are squaring the number. So it doesn't matter whether you are moving toward leftward or rightward, it will always remain independent of sign, and so will not vanish while taking the average. So we are left with r square comes out to be only the square terms of horizontal component and vertical component, and if we sum up the horizontal and vertical component of first step, say, and for second and for nth step, so what is this term in this square bracket? It is each term in square bracket in above equation is the length of the corresponding step in random walk. So this corresponding to first step is of which is equal to unity as assumed initially. So we have considered the unity step. So this comes out to be 1. Again for second step, again there is 1, and up to nth step we have another 1. So each one n times sum will give you capital N. So above equation becomes r square approximately equal to n. Why approximately? Because we are ignoring the cross terms. On taking square root of both sides of above equation, we obtained the desired root mean square radius or average distance. So r RMS, which depends on number of steps, is equal to square root of r square n, and it comes out to be approximately square root of capital N. So this is the simple result that characterize the random walk. So we have made a mathematical model for obtaining the average distance traveled by particle or average steps taken in a total number of steps of n averaged over m number of times. So it comes out to be square root of n for every iteration. So let us move on to the representation of random walk. I have already explained this kind of figure in the first slide. So this is a typical example of a random walk, irrespective of direction. Each direction has equal probability and step size is same. For example, say unity. So this kind of displacement can be explained with the help of random walk. So in this video, we discussed about what is actually the random walk. We have discussed about various examples of random walk, and we have developed a mathematical model, particularly for the two-dimensional case, that is for the plane. And we found that average distance traveled by particle or any body who is taking n step is equal to square root of capital N number of steps. So thank you everyone. Thank you for watching this video.